Hey there, welcome to the most fascinating topic in AI, deep reinforcement learning. My name is Thomas Simonini, and I'm a deep reinforcement learning engineer focused on implementing AI in video games. Since 2013 and the Deep Q learning paper, we've seen a lot of breakthrough, from OpenAI 5 that beat some of the best Dota 2 players of the world, to the Dexterity project. We live in an exciting moment in deep reinforcement learning research. And today, you have access to so many amazing games to build your agents. From Minecraft, OpenAI Retro, where you can train your agents on all Nintendo and Sega console games, to Unity machine learning agents that allows you to create your own environments and train your agents on it. That's why this is the best moment to start learning about deep reinforcement learning. And with this course, you're in the right place. Indeed, the video is the first chapter of Deep Reinforcement Learning Course version 2, which is a free course from beginner to expert, where you master the skills and architecture you need in order to become a deep reinforcement learning expert. In fact, during this course, you'll build a strong professional portfolio by implementing agents with TensorFlow and PyTorch that learns to play Space Invaders, Minecraft, StarCraft, Sonic the Hedgehog, and more. Also, because this course helps you to acquire the foundation of deep reinforcement learning, you will be able to work for any type of application other than games, for instance, dynamic pricing and trading agents. So you can check the syllabus of the course in the link above or in the description below. And if you're new here, don't forget to subscribe and ring the bell so that you don't miss the next video. So, in this first video, you learn the fundamental of deep reinforcement learning. It's really important to master this element before diving into implementing deep reinforcement learning agent. You can follow this video with the article version of this chapter by clicking in the link in the description below. So you ready? Let's get started. So, to understand what is reinforcement learning, let's start with an example. The idea behind reinforcement learning is that an agent, an AI, will learn from the environment by interacting with it through trial and error and receiving rewards that can be positive or negative as feedback for performing action. In fact, learning from interaction with the environments comes from our natural experiences. For instance, imagine you put your little brother in front of a video game he never played and you give him a controller. You let him alone. What's going to happen is that your browser will interact with the environment, so the video game, by trying actions and seeing the results. In our case, it will try to press right, so it will take the action to go to the right, and it will see that he will get a coin, and so a positive reward one. Thanks to this first experience, he understood that he needs to get the coin. But then he press right again, and in this case, he touches the enemy, so he just die, -1 reward. What we see here is that by interacting with this environment through trial and error, so by trying action and seeing the results, your little brother just understood that in this environment, he needs to get the coin, but also he needs to avoid the enemies. So it means that without any supervision, the child will get better and better at playing the game by interacting with it through trial and error. And in fact, that's how humans and animals learn through interaction. So reinforcement learning is just a computational approach of learning from action. So now, if we take a formal definition, reinforcement learning is a framework for solving control tasks, also called decision problems, by building agents that learn from the environment, by interacting with it through trial and error, and receiving rewards that can be positive or negative as a unit feedback. So now that we understood what is reinforcement learning, let's see how it works. So this diagram is a reinforcement learning process. It's a loop of state, action, reward, and next state. But to better understand it, let's take an example. Let's imagine an agent that learns to play a platform game. In our case, the reinforcement learning loop goes like this. First, our agent receives a state from the environment. So we receive the first frame of our game, of our environment. Based on that state, the agent will take an action. So in our case, our agent will move to the right. Environment will transition to a new state, a new frame, because we move to the right. And the environment will give some reward to the agent. So in our case, we're not dead, so reward +1. And this reinforcement learning loop outputs a sequence of state, action, reward, and next state. And the goal of the agent is to maximize its cumulative reward called the expected return. So you may ask why the goal of the agent is to maximize the expected return. It's because reinforcement learning is based on what we call the reward hypothesis, which is that all goals that an agent can have can be described as the maximization of the expected return. So that's why in reinforcement learning, to have the best behavior, we need to maximize the expected cumulative reward. Also, something important you're going to see in some papers is that the reinforcement learning process is also called the Markov decision process. So, we'll talk again about the Markov property in the next chapters, but if you need to remember something today about it, is that Markov property implies that our agent needs only the current state to make its decision, not the history of all the state and action it took before. So what it means that it simplifies the reinforcement learning problem because it means that an agent, in order to take a decision, take an action, just only need the current state and not the history of all state and all action it took before being at that state. So now that we define the reinforcement learning process, let's dive a little bit on all this new vocabulary. So we say that the first step of the reinforcement learning loop is the agent that receives the state. So, states are the information our agent gets from the environment. In the case of a video game, it can be a frame, a screenshot. In the case of a training agent, it can be the value of a certain stock, but there is a differentiation to make between observation and state. In the case of state, we are in a case of complete description of the state of the world. There is no hidden information. So it means that we are in a situation of a fully observed environment. So if we take the game of chess, we receive a state from the environment because we receive the whole checkboard. There is nothing hidden. That's why we call it a state. An observation, it's a partial description of the state of the world in a partially observed environment. So, for instance, if we take in Super Mario Bros., we only see a part of the level close to the player. We don't see the whole level, so we don't receive the whole level. So, we receive an observation. But something important to consider is that in reality, we only make this distinction in implementation. Most reinforcement learning courses use the term state when they explain something, but do the distinction in the implementation. And it's what we're going to do. We're going to speak about state every time, but when we're going to implement, we'll make the distinction. So we saw then that the second step of reinforcement learning loop is that the agent, given a state he got from the environment, chose an action. So the action space is a set of all possible action in an environment. The action can come from a continuous space or a discrete space. So in the case of a discrete space, the number of possible action is finite. If we take again the example of Super Mario Bros., we have a finite set of possible actions since we have only 4 directions and a jump button. On the case of a continuous space, it's when the number of possible action is infinite. For instance, if you take a self-driving car agent, he can have an infinite number of possible actions since he can turn left at 20 degrees, 21, 22, honk, turn right, etc., etc. And in fact, knowing if we are in a discrete or continuous space is crucial because it will have an importance when we choose a reinforcement learning algorithm. The third step of the reinforcement learning loop was receiving a reward from the environment. And the reward is fundamental in reinforcement learning because it's the only feedback for the agent. Thanks to it, the agent will know if the action taken was good or not. The cumulative reward at each time step, t, can be written like this. It's equal to the sum of all rewards of the sequence. However, in reality, we can't just add the reward like that. Because the one that comes sooner, so at the beginning of the game, are more probable to happen since they are more predictable than the long-term future reward. So to understand this concept, let's say that your agent is this small mouse in this game. Your mouse can move one tile each time step, and your opponent is a cat that can move two. In this case, your goal is to hit the maximum of cheese before being hidden by the cat. As we can see in this diagram, it's more probable to eat the cheese near us than the cheese close to the cat because the closer we are to the cat, the more dangerous it is. As a consequence, the reward near the cat, even if it's bigger because there is more cheese, will be more discounted since we are not really sure that we'll be able to eat it before the cat eats us. So, to discount the reward, we'll process like this. First, we'll define a discount rate called gamma. It must be between 0 and 1. It means that the larger the gamma, the smaller the discount. This means that our agent will care more about the long-term reward than the short-term reward. On the other hand, the smaller the gamma, the bigger the discount, and in this case, it will mean that our agent will care more about the short-term reward than the long-term reward. Then the second step is that each reward will be discounted by gamma to the exponent of the time step. So, to better understand that, let's take the formula. What we see here is the expected cumulative reward. It's the sum of the reward discounted by the gamma to the exponent of the time step. We need now to speak about the task. So, a task is an instance of a reinforcement learning problem. We can have two types of task, episodic or continuous. So, in the case of an episodic task, we have a starting point and an ending point, also called a terminal state. This creates an episode. It means a list of state, action, reward, and new state. For instance, think about Super Mario Bros. An episode begins at the launch of a new Mario level and ends when you're killed or when you reach the end of the level. On the other hand, continuous tasks are tasks that continue forever. It means that there is no terminal state. And in this case, the agent has to learn how to choose the best action and simultaneously interact with the environment. For instance, if you create an agent that does automatic stock trading, in this task, there is no starting point and no terminal state. So it means that the agent keeps running until we decide to stop him. Finally, before looking at the different methods to solve reinforcement learning problem, we must cover one more very important topic, which is the exploration trade-off. So exploration is exploring the environment by trying random action in order to find more information about the environment. On the other hand, exploitation is using non-information to maximize the reward. So remember that the goal of our reinforcement learning agent is to maximize the expected cumulative reward, also called the expected return. However, we can fall into a common trap. So let's take this example. So what you see here is a game where a mouse can have an infinite amount of small cheese. The reward is +1 each. There is a gigantic sum of cheese where the reward is +1000. However, if we only focus on exploitation, our agent will never reach this gigantic pile of cheese because instead it will only exploit the nearest source of reward, even if the source is small, because it will do only exploitation. But what we see here is that if your agent does a little bit of exploration, it can discover this pile of cheese because it will take random action that will push him to discover a new part of the environment. And it implies that at one moment, it will discover this big pile of cheese. This is what we call the exploration-exploitation trade-off. And what it implies that we need to balance how much we explore the environment and how much we exploit what we know about the environment to maximize the return. So it means that we must define a rule that helps to handle this trade-off. And we'll see in the future videos different ways to handle it. So if it's still confusing, think of a real problem, the choice of a restaurant. In this case, exploitation will be going every day to the same restaurant that you know is good, but take the risk to miss a better restaurant. On the other hand, exploration will be trying restaurants you never went before, with the risk of having a bad experience, but the probable opportunity of having an amazing experience. So now that we learned the reinforcement learning framework and the important concept associated with it, how do we solve a reinforcement learning problem? In other terms, how do we build a reinforcement learning agent that can select the action that maximizes its expected cumulative reward? So in order to answer this question, the first thing we need to understand is a policy. So the policy is the brain of our agent. It's a function that tells what action to take given the state we are. So it defines the agent behavior at a given time. Think of policy as the brain of our agent, the function that will tell us what action to take given a state. It's what we see in this example. We give a state to our policy and it outputs an action. This policy is a function we want to learn, and our goal is to find the optimal policy. It means the policy that maximizes the expected return when the agent acts according to it. And the question we can ask is, how do we find this optimal policy? In fact, we find this optimal policy through training. So there is two approaches to train our agents to find this optimal policy. The first is directly by teaching the agent to learn which action to take given the state it is. It's called policy-based method. Or indirectly, which is teaching the agent to learn which state is more valuable and then take the action that leads to the more valuable state. We call this type of method value-based methods. So, to understand better, look at this example. On the one hand, we want to learn a policy that indicates what action to take to get out of this maze for each state. On the other hand, we learn a value function that will indicate what value each state has, and we just need to take actions that leads to the highest value. So we see here two main methods to solve the reinforcement learning problem, but we'll see in the future that there is other methods such as model-based or hybrid methods. But for now, let's dive deeper on these two methods. In policy-based method, we learn the policy function directly. This function will map for each state to the best corresponding action at that state. What we see here, in order to get out of the maze, it shows what action to take at each state. In fact, it can be also a probability distribution over the set of possible action at that state. So it implies that we have two types of policy. The first is deterministic, so it's what we just saw with the example. It's a policy where at a given state, it will always return the same action. For instance, what we see here is that given the state, our policy will take the action going to the right. The second type of policy is stochastic. So in this case, the policy outputs a probability distribution over action. It's what we see here in this example. We pass this state, and the stochastic policy outputs a probability distribution over action. It means that you will not always take the same action, since there is a probability of taking each of the possible action. So now, in value-based methods, instead of training a policy function, we train a value function that maps a state to the expected value of being at that state. So in fact, the value of a state is the expected discounted return an agent can get if it starts at that state, and then act according to our policy. So what means act according to our policy here? It just means that our policy will be going to the state with the highest value. To better understand, let's take again this example. So what we see here is that our value function defines a value for each possible state. And what we say is that the value of a state is the maximum expected cumulative reward I can get starting at that state. So you may ask here why it's only negative value. Something I forgot to say is that in this environment, our goal is that the agent will go fast from the beginning to the maze to the end. So we want to push him to go fast. How we do that? We put negative reward at each time step. Why we put negative reward at each time step? Because we know that our deep reinforcement learning agents wants to maximize its expected cumulative reward. So if we put negative reward, his goal is to have the less cumulation possible of negative reward. That's why here is -7, because the value of this state is the cumulative expected reward starting at that state. For simplicity, we will not discount. So here, why it's -7? Because if we calculate, it's -1. The reward here is -1, -2, -3, -4, -5, -6, -7. That's why it's -7. And what we see here is that thanks to our value function, at each time step, our policy will select the state with the biggest value defined by the value function. So here, if we go to the right, go to the the state with the highest value. But here he has the opportunity to go down, left, or right. But because he wants to go to the state with the highest value, he will go again to right, -5, then to -4, then to -3, then to -2, and then to -1 in order to get the goals. So thanks to our value function, at each step, our policy will select the state with the biggest value defined by the value function. Again, if you still feel puzzled about the difference, don't worry because we'll dive deeper on both methods in the next videos. So the last point we need to speak today is why we speak about deep in deep reinforcement learning. So, in fact, deep reinforcement learning introduces deep neural network to solve a reinforcement learning. That's why we use the term deep. For instance, in the next article, we're going to speak about Q-learning, which is a classic reinforcement learning algorithm, and then deep Q-learning, and both are value-based reinforcement learning algorithms. So you'll see that the difference is just that in the first approach, we use a traditional algorithm to create a Q table that outputs a value. And on the deep Q-learning approach, which is a deep reinforcement learning approach, we're going to build a neural network that will approximate the value. So if we summarize simply, in the term of deep reinforcement learning, we use deep neural network to approximate, if it's a case of value-based method, a value function. If it's a case of policy-based method, to approximate a policy function. So this implies that you need to have some skills in deep learning in order to follow the rest of this course. If it's not the case, there is a very good course called MIT Introduction to Deep Learning, which is free, and it will give you everything you need to know about deep learning for this course. I put the link in the description below. So that's all for today. Hope you liked the video. Congrats on finishing it. That was the biggest one. There was a lot of information. So that's normal if you feel a little bit confused with all these new elements. This was the same for me and for all people who studied reinforcement learning. So what you need to do is to take time to really grasp the material before continuing. It's important to master this element and have a solid foundation before entering the fun part, which is creating AI that plays video game. And if you enjoyed the video, don't forget to like it, to subscribe, and to ring the bell so that you don't miss the next video. And if you have some feedbacks and questions, please write them in the comments section below. In the next video, we're going to learn about our first reinforcement learning algorithm, Q-learning, and dive deeper into the value-based method. You'll train your first reinforcement learning agent, a taxi that will need to learn to navigate in a city to transport its passenger from point A to point B. This will be fun. Again, thank you so much for watching, and I'll see you next time and in the comment section below. Keep learning. Stay awesome.